Today, today we're going to start going over piecewise functions. So piecewise functions are something that you guys have actually seen before. We evaluated piecewise functions earlier this unit, and now we're going to actually create the graphs of them. So I know these equations look kind of crazy, but just to remind you what a piecewise function is it basically divides the graph up into 2 or 3 or 4 or 5, however many parts. And there's different functions that tell the graph what to do at different parts. So if you look at this particular example, the first equation, this is a quadratic. And I know that because it is x squared. So part of this graph is going to be a U shape, a quadratic. If you look at the second part, it's an absolute value function. So part of the graph is going to be a V shape, and they'll come together to create the piecewise function. There's lots of ways to graph these piecewise functions. What I prefer to do is I use a lot of tables. So what I'm going to do is first look at this function, and I'm going to create a table for it. And I'm just labeling it with whatever that line said. So x squared plus 2, x is greater than 3. And again, I'm making a table here. All right, so let's talk about this number right here. So this number, which is 3 in this particular case, is always going to be the first x value we put in the table no matter what, whatever's in that inequality. Then if you read the inequality, it says x is greater than 3. So we're going to choose a few numbers that are greater than 3. So we're just using that inequality to help us drive what we're doing here. Now to come up with the y values, we're going to plug these values in for this x. So if I plug in a 3, 3 squared is 9 plus 2 is 11. And then if you plug in a 4, 4 squared is 16 plus 2 is going to be 18. Notice how these numbers are going off the graph. So 5 squared is 25 plus 2 is 27. So we're just going to do the best we can to graph what we have. So number 6, or if we plug in a 6, 6 squared is 36 plus 2 is 38. Now if we go to graph what we have here, again this is going to go off the graph, but I want to talk about this point right here, 311. If you look at our inequality, notice it says that 3 is not included in the inequality. There's no equal to part here. So the way that we're going to represent that in our graph is to make an open point at 311. And again, I'm just going to do the best I can. I know this goes off the graph. That's okay. 311 would be right about there. And then 418 would be much further up here. So our graph, it's a quadratic, so notice I have like a little bit of a U shape, and that would be the first part of our graph. Now the second part of our graph is ruled by this absolute value. So this 1/2 absolute value of x minus 4 when x is less than or equal to 3. So I'm going to make an xy chart, just like I did before. And remember, I started my xy chart with whatever that number is, which in this case is a 3. Then read your inequality. Your inequality says x is less than or equal to 3. So I'm going to pick some numbers that are less than or equal to 3. And then just like I did in the first case, I'm going to go ahead and plug these numbers in for x and see what I get out. So if I plug in a 3, 3 minus 4 is -1. The absolute value of that is +1. 1/2 times +1 is 1/2. If I plug in a 2, 2 minus 4 is -2. The absolute value of that is +2. 1/2 of 2 is 1. Continuing down that line, if I plug in a 1, I would get 1/2 times 3, which is 3/2 or 1.5. And if I plug in a 0, I would ultimately get out a 2. So starting at 3, I'm up here at 1/2. Now, Let's talk about this 0.3 like we did before, that top point. Think about, is 3 included in this inequality? In this case, it actually is. So we're going to make this a closed, which is just a normal point at 3/1/2. So at 3/1/2, do the best you can to plot that. Then 2, 1, 1, 1.5, and then 0, 2. So this actually looks a little bit like a linear function, which does make sense because part of an absolute value function, if you just have half of it, it does look linear. Now what I want to show you guys, so this is finished, but what I want to show you is kind of the bigger picture of this particular graph and like what's happening here. So I want to go back to that quadratic, the x squared plus 2. If I were to just graph x squared plus 2, it would have a vertex at 0, 2. And here are my points. So notice what we graphed was just a slice of this whole quadratic. And it was that upper end of it on the right side. For the absolute value function, this vertex is at 4, 0, and it has a slope of 1/2. So I'm graphing that. And you can see that we have the left end of that. So we're just taking parts of these entire graphs. It's nothing new, nothing that you guys haven't done before. You've graphed a quadratic, you've graphed an absolute value, but it's just giving you just a snapshot, zooming in on a particular part of that graph. I'm going to go ahead and delete what I did in green because that would not be part of your final answer. I just wanted to show you that. So this would be your final answer. Okay, so continuing on B, we have a quadratic and we have a linear function that's ruled by -3. So same strategy here. I'm going to start with this top line. And we're going to go ahead and make a table for that. So I'm carrying it over here. So remember, when I made a table, the very first number I put in my table was the number in the inequality. And then it says x is less than or equal to -2, so I'm going to pick some numbers that are less than -2. I'm going to plug them into the equation and see what I get out. So if I plug in a -2, that would be 2 squared, which is 4, times -2 is -8. And if I plug in a -3, I get 1 squared, which is 1, times -2, which is -2. This would be 0. And if I plug in a -5, I get out -2, I believe. All right, so that's our first part. So remember, think about this top point. Is it open or closed? Look at your inequality. It says equal to, so this is going to be a closed point, which again is just a normal point. So we have a normal point at -2, -8. Then -3, -2. -4, 0. And 5, -2, -5, -2. You can really see the quadratic starting to come together here, so you could actually even continue that pattern here. But what I want to remind you of is when I connect these points, if you remember this first point that I'm going to start at, this piecewise function only goes in one direction. So notice I didn't continue past that first point. It started there and then bounce through the other points and continue to the left, but it doesn't go to the right any further because this quadratic only applies when x is less than or equal to -2. So that first point that I was talking about is a closed point, -2, -8. You could also refer to it as the starting point. Okay, so moving on to the next part of this graph. We have a -3 when x is greater than -2. So again, remember, we always start our table with whatever values in the inequality. And notice it's the same in both cases, so both of these tables start at -2. And it says x is greater than -2, so I'm going to pick some numbers bigger than -2. And we're going to plug them into the equation. So this is kind of an interesting equation because the equation is just -3. There's no x to plug a value into. So I'm going to go ahead and say the output will always be -3. And that's always the case if you don't have an x, it's whatever the value is. Thinking about this top point, if it's open or closed, it is going to be open since that inequality does not have an equal to part to it. So we have -2, -3, and it's an open point. Then we have -1, -3. And again, it starts at that first point and goes through the other points. So I didn't expand this in both directions. The next thing that I just want you to observe here is notice that this graph is a function because we call them piecewise functions. So it passes the vertical line test. A really good indication if you've made a mistake on your piecewise graph is if it doesn't pass the vertical line test. So always check that because even at the value of -2, we have an open point and a closed point, which we've seen before, and that still passes the vertical line test. Okay, so our last one here, because we're just going to do target 12 today, we're going to do 14 and 15, or sorry, 13 and 14 next week. So don't worry about those. You're just going to stop your notes here. Notice that this graph has 3 different lines, but don't let that scare you. We're going to approach it the same exact way, starting with this first line. So this is a linear function, x plus 2 All right, so we start our table at the x value of 2, since that's what's in the inequality. And it says x is greater than 2, so picking some numbers bigger than 2. And then we plug them into the equation. So x plus 2, so if I plug in a 2, I would get out a 4, then a 5, 6, 7. Thinking about that first point, our inequality does not say equal to, so this is an open point at 2, 4. And then from there we have 3, 5, 4, 6, 5, 7. So we started at that first point and we continue on through the next few. I'm actually going to skip that middle part here for a second, and I'm going to go to this last part. So we have the absolute value of x minus 4. X is less than -5. So we're going to make our xy chart. This inequality has a -5 in it, so we're going to start at -5. And it says x is less than -5, so let's pick some numbers that are less than -5. And we're going to plug them into our equation. So if I plug in a -5, I get the absolute value of -9, which is 9. If I plug in a -6, I get the absolute value of -10, which is 10. Then that would be 11 and 12. And again, thinking about that top point, because this doesn't have an equal to part to the inequality, it would be an open point at -5, 9. Oops, I just said open and made it closed. And then at -6, 10. And then it goes off of our graph, so -7, 11. And if you want to continue up, you can. It starts at that first point, goes through the next 2. And remember, this is a absolute value function. And so it looks like a line there, but it's just because we're looking at part of the absolute value. So we don't see the bounce back part that our absolute value function does have. If we graphed the whole thing of x minus 4, the absolute value of it, we would see that V shape. Okay, coming back to this middle line here. So we're going to make a third table since we have a third line. Our inequality looks a little strange here. Here's our table. Now, if you remember, in our previous tables, we've always used the numbers that were in the inequality. So look at your numbers in the inequality. We have a -5 and a 2. And in this case, it's actually easier because we're just going to pick the -5 and the 2. And so I'm going to plug in a -5 for x. I would get out a -1. And if I plug in a 2, I get out 2/5. Now before I plot these points, I have to think about if these points are going to be open or closed. So look at both of these inequalities. Both of them are equal to, so both of these are going to be closed points or normal points. So we have -5, -1, and we have 2/5, and we're just going to do the best we can to plot that, and we're going to connect them. Notice in this case, we don't extend indefinitely in either direction. It starts at -5 and it ends at 2. If I extended it past that, we wouldn't have a function because it wouldn't pass the vertical line test. So we just start and stop. And again, it is a function. It does pass the vertical line test. So that's graphing a piecewise function. And we're going to talk more about piecewise functions next week. You can ignore this domain and range. We are going to talk about that next week. So on your homework, you're just doing target 12. Ignore the 13 and 14 part for now. We're going to come back to that.